So I'm here to talk to you today about the various sort of pointy edges of Go, the things that you might trip you up as you're programming in Go and your careers. And I realized when I was making these slides that I actually was missing a subtitle. There's a lot of problems that you can run into at compile time, but obviously the compiler is there for you. It's going to tell you immediately when you've made those mistakes. But there are other things that you can do that you might not realize you're doing until you actually have something out there and running in production. So I'll discussing some of the runtime problems that can trip you up. But before I go into some of the examples, I want to talk a little bit about the simplicity of Go. Go is a simple language, simple in both design and in lexical elements. In his keynote, Russ laid out the reasons for this, so I won't really go into that, but let me just provide one little bit of evidence for that. This is the keyword space of Go from the ref spec. It's only 25 keywords. That's it. That's everything. And keywords for a language are really the foundation, in my opinion, and they sort of lay the groundwork for all of the things that you kind of have to think about, and the kind of things you have to learn, and the edge cases get more complex with the more keywords you have. So understanding the keywords of Go, I think, is really important. Understanding what they do, and also like what are the weird things that they do that you might not expect. And just for comparison, some other popular languages, number of keywords. Python's pretty close. Ruby's a little bit worse. You see Java, and then C++. I mean, that's like 3 times the number. Yeah, I put C++ at the end there. I know everybody's got to burn the C++ books, right? So I just sort of like one little sliver of evidence for, the thought and care that was really put into, I should really say like the discipline that was taken in not bloating the language itself. So because Go is simple lexically, there are really fewer specifications to know about. And I would argue comparatively fewer things that really can go wrong. But let's break some stuff anyway. Okay, so the first example here is one that's probably familiar to most of you. This is arranging over strings. Strings in Go are, like the code, or the code itself is UTF-8 and the strings are UTF-8. And when you range over strings, you're arranging over the Unicode code points of the elements of that string, which might not be expected if you knew that strings are just byte slices underneath the covers. So when you range over something like this, and I have I Heart New York, you're seeing an individual iteration for every code point. That's only 6 iterations. But if you were to actually range over the byte slice representation of the same string, you're going to iterate 8 times. And that's because the heart is really 3 code points, or 3 bytes, represented by 3 bytes. And I printed out the the Unicode values as well as the literals, so you could see them sort of represented. And if you didn't know that, or if you expected it to behave the same across all types that you might range over, you could get tripped up here. But really, not a big deal. Speaking of ranging, ranging over maps is interesting. Most of you probably know that ranging over maps is going to be somewhat a randomized order. Maps themselves are not guaranteed to be in any specific order. There might be some implementation consistency in the ordering of maps, but when you're ranging over them, they're actually explicitly randomized so that nobody actually gets comfortable with the idea that maps might be ordered when they're definitely not. In this particular example, I'm modifying the map as I range over it. This can be dangerous. The ref spec says that if map entries are created during iteration, that entry may be produced during the iteration, or it may be skipped. So what that translates to is kind of shrug. You really don't know what's going to happen to the map while you're modifying it and you're iterating it over at the same time. So if you're going to do something like this, I would advise you to either copy the map or do the modifications after you're done with the iteration. You can also get into trouble when you're ranging and using closures at the same time. Now, just to sort of like preface this, I just want to point out how closures really do their enclosing. So in this simple example, we have a function foo which encloses val. And as we execute calls to foo, if we change val in between, the output of foo is also going to become different. That's because when you're enclosing val, you're actually enclosing a reference to val. It's not a copy. So if you're doing an iteration in a range loop, like this one, you can get weird results. In this particular case, the Go routines haven't even started to execute by the time V has been assigned its final form, which is C. It just loops right through, V becomes C, and every single closure gets the same reference to the same value of V. And that's because range loops use the exact same value as they iterate, and they assign it over and over again to the same value. So if you know that, you kind of know you're in a way dealing with pointers here, but it doesn't look like pointers. The fix is, of course, pretty easy, and in my opinion, much more legible. You don't enclose them, you just pass them in. In this case, you pass V into the function, V becomes copied to you, and now you've got a new value every single time. And you're never going to run into this problem. I'm pretty sure GoVet will catch this kind of problem for you, so make sure you're using the tools. And this, of course, is also valid. This one seems a little strange, and to me it is, but it's perfectly fine. And if you look in the Go FAQ, you're going to find an example almost exactly like this. So if you really want to use closures, there you go. So let's take a look at something a little bit more nuanced than this. And these are something called typed nils. And if you're not familiar with the way nils work in interfaces in Go, they're sort of special. So in this particular program, we're doing the standard thing that we always do. We're just doing an error check. If error is not equal to nil, panic or do something. And we have a function called check error, which returns an interface of error. Let's take a closer look at check error. So in this implementation, we have foo error, pointer to foo error, which implements error. It's an error. It satisfies the error interface. But the first thing we're doing in check error is we're setting ourselves up for failure by declaring error as a typed pointer to foo error. Now, an interface value is nil only if both the underlying type is nil and the underlying value is nil. It doesn't matter if the underlying type is not nil, it doesn't matter if the value is nil or not. It will never evaluate to nil. So in this particular case, we can't possibly return a nil error. It will always be non-nil, and our program will always panic. So the easy way to get around that is just declare your error as an interface itself, or better yet, return the identifier nil any time you want to actually return a nil error. I ran into this problem maybe like 3 or 4 months into my experience with Go. It took a while. I guarantee you'll probably run into it at some point if you haven't already. You'll want to do something clever. You want to have like a type. You want to do something inside the scope of check error. Just make sure if you're doing something like that, you're always returning nil, the identifier nil. So this one was covered in Richard's talk as well earlier today, but this is a good one. And I make this mistake still like occasionally without thinking about it. Anytime you have a function that doesn't return, your defers are useless. So, an iteration like this, especially when you're creating connections and you're not closing them, you're going to run into all kinds of problems, the least of which is going to be your memory. But of course, again, super easy to fix. Just wrap it in a function, an anonymous function. If you do this, every single time the function executes in the iteration, it will return and it will execute defer. Defers are executed right before the return, so yeah, this works perfectly well. Can we do better than this? Maybe. This one to me is a little bit better. Just because we have a keyword of defer doesn't mean you actually have to use it. So this is perfectly fine and something you would see in any other language, and there's no reason not to do your cleanup this way. I kind of like this because it keeps the indentations to a minimum, makes things a little bit readable, but it's really just a judgment call. Okay, slices are not arrays. We probably don't use arrays all that much. I know I don't. I probably used arrays maybe 3 times in the 1.5 years that I've been using Go. But slices are king, right? Like we use them everywhere. They're really, really useful. They're really flexible. So if you have a function like this where you're passing in arrays by reference and you're modifying them and you're expecting like things to be changing all the time, if you ever run into a case when you want to switch these to arrays, you might expect them to work the same way, but they will not. Arrays are values in Go. They're not pointers to a value. They're not like slices that point to an array segment. They can be modified by reference. A similar function in arrays is essentially a no-op. Something like this is, going to be pretty clear when you see the results, but you may not realize it. It's not going to cause a compilation error. Runtime will just give you the results you don't want, but you won't know until sometime later. And in my experience, like I said, they're not used that much, but it's all the more reason to understand what's happening, because when it does happen, it's going to bite you. So be a little bit careful with arrays. This is a fun one. So Go does not really provide the typical type-driven notion of subclassing that you have in other languages like Java, but it does allow embedding of types. In embedding here, I've got a type bar which embeds foo, and they both implement the exact same signature val. Now, if you're not aware of what foo's methods are, you may not realize, or if you're not aware that like they're sharing the same method, you may not really realize which one you're trying to invoke. And so if you really want to invoke foo's val, you're going to have to explicitly call foo as a field and then call val on it. Of course, the exact same thing is true with fields, not just functions. Same example, but just with fields. I occasionally run into this because I like to name fields the same in a lot of my types. I use name as a field name a lot. I use ID, user ID. If you're embedding types, you can get into a little bit of weirdness when you're dealing with that kind of thing. All right, let's talk about concurrency a little bit. So this one is a very, very simple, very, very bad thing that you can do. We have 2 channels, A and B, and they're both receiving, they're both sending on the channels in the Go routine, and then we're selecting on them. Now the problem here is that we never actually receive on B. A gets selected and B gets ignored, and so the Go routine is sitting there trying to send on B over and over again. It just sits there, it gets blocked, and nothing can happen. The memory model is pretty clear on this subject. A receive from an unbuffered channel happens before the send that the channel completes. So without someone asking for something, you can't give anything. And that's really only applies to unbuffered channels. So the solution, again, is simple. Just buffer the channel. If you do that, then nobody's receiving on B, but the function can return, the memory can be cleaned up, and things can move on. I find that whenever I have some lock somewhere in my code, it's often a case of an unbuffered channel. We tend to create channels willy-nilly, sort of like it's so easy to do concurrency in Go that we tend not to think too deeply about what's actually happening or what might be happening. So just be aware. All right, it is possible to block the scheduler in Go. As many have said before, over and over again, a concurrency is not parallelism. With Go max proc set to 1, your Go routines are scheduled for execution in a single operating system thread. And what that means for you is that scheduling can be blocked, preventing any concurrency from happening. In this example, what we have is a very greedy function called iterate, and all it does is loop through and print the iteration value over and over again. But while it's doing that, nothing else can run. No other Go routine can schedule, no other Go routine can execute. It takes over completely. And then that program exits, and our poor little Go routine never actually gets a chance to do anything. There are several ways to deal with this, but one of them, which is very, very explicit, is to yield to the Go scheduler. And you can do that in the runtime package. There's a function called GoSchedule. And if you have a greedy function like this one, in an iteration loop, you can always just invoke the Go scheduler and it will yield allowing Go routines to run. It's also kind of nice because it really provides a sort of a clear indication that you know that this loop or this routine is kind of greedy and kind of doing things in a very greedy way, and it lets the next person know what's happening. You can also, by the way, achieve this with like a sleep, like a very, very short sleep, but I kind of like this solution better. Oh man, I'm going so fast. All right. So this is an interesting one. I love this idea that of pre-declared identifiers in Go. I didn't really think about them too much, but remember the keywords I was talking about at the beginning? There they are. Well, you might have noticed something's missing from these keywords, specifically int, float64, true, false, iota. We all kind of think of those as reserved words in Go, but they're not. They're just something called pre-declared identifiers. They're just pre-declared. They're just pre-declared by the language. And then they're made available globally. So that leads, there they are, here. There's the whole list of pre-declared identifiers. Again, not that many, but the fact that they're pre-declared is interesting. And it got me thinking, and I was like, okay, well, if they're all pre-declared, can they be redeclared? And the answer to that is yes. So in this simple example, I've got a delete function I'm deleting a key on a foo map, and then I'm checking to see if that key exists. You know, it works as expected. But there's nothing stopping me from doing that. So in my implementation of delete, I'm very cleverly just setting the key to the 0 value. I'm not actually deleting anything. So if I put that in a package somebody else calls delete, they're not going to know. They're not going to understand why it's not behaving the way it's behaving. So this, of course, now opens the door to some interesting stuff, right? So if I can do this with delete, and by the way, I don't have to do anything to the map here. I could just ignore it. I could print foo. You know, I could add things to the map. I could do whatever I want. But I can also do weird things like that. And I can redeclare true as a type. Sure, why not? And then I can cast false into it, print false. I can do whatever I want. And if you really want to give your coworkers play a true prank on your coworkers, you can really just flip the script totally and just switch things around all you want. So this is what I like to call WTF.go. So to be honest, like this stuff here, like the pre-declared identifiers and messing with this kind of stuff, although weird, I've never ever run into a problem with that. I've never actually had a case. This is the only slide on the whole talk where I'm demonstrating something that I've never actually run into. But I think it's really good to know what the language allows for. And if you know what the language allows for, you're going to really understand a lot more about what it's doing and how it works and how to predict what your own code is going to do when you write it and avoid these things in the future. So is that it? I mean, is that all of it? Kinda. I mean, I just want to put into context here that there's not much more than this that can really go wrong at runtime. Everything else that might go wrong is going to be, user, picnic stuff, problem in chair, not in computer. This is the only stuff that I've really run into that's somewhat surprising to me. Although, to be honest, I really shouldn't be that surprised. Everything that's been up here, every single thing up here, has a reference or a mention or is somehow addressed in either the ref spec, the Go blog, effective Go. I mean, the documentation is there. It's just there to read. And we've been using Go at TimeHop for over a year and a half now. We've had dozens of services dealing with millions of active users a day, and these are pretty much the only things we've ever really run into. There's a few others, but they're not much. They're really more just like derivatives of these ones. Wow, I went really, really fast. Okay, well, that's pretty much it. I hope you guys learned something. new, whether you're new to the language or whether you've been using it for a while. And when you do run into these things, and you are going to run into them, hopefully this will come back to you in your memory. Thank you all so much for listening. It has been an honor and a privilege to be up here, and I want to thank Kelsey and Brian and Eric and all the other organizers of GopherCon. It's really awesome. So thank you, everyone. And I've got like 10 minutes now for questions. I've really screwed myself. So I guess question time. Yeah.